Before we look at the divergence theorem, we're going to remind ourselves that we have seen a vector form of Green's theorem, and that is that the line integral over c of f dot n ds is equal to the double integral over d of the divergence of f at xy times dA. This is on R2, and the divergence theorem is going to give us a similar result, but in R3. That is, the divergence theorem is like a 3D analog of Green's theorem. To start building the theorem, we consider E as simple solid region, and S is the boundary surface of E with a positive orientation. Remember that for closed surfaces, a positive orientation means outward pointing normal vectors. We're also considering a vector field F whose component functions have continuous partial derivatives on an open region that contains E. With these requirements in place, the surface integral over S of f dot ds, so the flux, is equal to a triple integral over E of the divergence of f dv. So for both Green's theorem and the divergence theorem, on the left-hand side we have the surface integral over S of f dot ds. On the right-hand side we have the divergence of f, but now we're in a higher dimension, so we have a triple integral and it's dv instead of dA. What this means is that the total flux into or out of E, so this triple integral, is equal to the net flux across simply the boundary surface of S. Now, as far as the integrand here that has divergence of f, recall that divergence at P describes fluid flow at P. And it's the case that if the divergence of f at a point P is positive, then net flow is outward. And P is called a source. If the divergence of f at a point P is negative, then net flow is inward and P is a sink. And remember, if divergence is equal to 0, then the fluid is said to be incompressible. As for the proof, I'm going to walk you through what we have in the textbook. If f is pi plus qj plus rk, then the divergence of f is going to be the partial of p with respect to x, the partial of q with respect to y, the partial of r with respect to z, and so the triple integral is expressed as the sum of three integrals. Turning to the left-hand side, that's that flux integral over the surface S. We're splitting apart p, q, and r into the sum of three integrals that have pi dot n, qj dot n, rk dot n, ds, and all three of them over s. And so, again, similar to Green's theorem, what we're after is being able to show, for instance, that the third triple integral from the divergence expression is equal to the third double integral for the flux expression. The approach that our author is using is that E is a type 1, type 2, and type 3 region, which means all the boundaries can be expressed as functions. In particular, Z is between two functions. We'll call them U1 of xy and U2 of xy. Considering dv as dz times dA, we can evaluate the inner integral integrating with respect to z, and the derivative and the integral effectively cancel, and we end up with r evaluated at xy u2 minus r evaluated at xy u1 inside of the integral with over the region D, the double integral, dA. Now, setting that aside, because that was the triple integral portion, now what we're going to do is look at how we can express the double integral and hope we get the same thing. Considering this as a type 1 region, we have a top surface and a bottom surface, S2 and S1 respectively. If there is a vertical face around the whole thing, which by the way wouldn't be the case in the event that we had a sphere, for instance, then its normal vector points parallel to the xy plane, and dotting that with k would give us 0. So we only have to consider S1 and S2. Over S2, we're considering rk dot n ds, and using a result from a previous section that's expressed as the double integral over d of r evaluated at xyu2 dA. We have a similar result for S1, but the normal vector points downward. And so we have the same double integral, except it's got a minus sign out front, and we're at u1 because we're talking about the bottom surface. Combining the two gives us the double integral over d of r evaluated u2, minus r evaluated xyu1. And this is the same result that we got looking at the triple integral. Doing the same thing for P and Q would give us the proof of the divergence theorem. The divergence theorem was stated here for a simple solid region E. That means it's got no holes inside of it. But in the event that E lies between two closed surfaces, we can extend the divergence theorem. Let's say the surfaces are S1 and S2 with S2 inside S1. In that case, N1, the normal vector for S1, points outward, but to make N2 point inward, we actually use the negative of N2. What do we mean pointing outward and inward? Well, suppose we have here a surface S1, and inside of it is a surface S2. And these are surfaces, so let me give this some dimension. So I'm kind of thinking like a jelly donut where the inside is hollow instead of a jelly. An outward orientation for N1 makes sense, it'll point outward, but an outward orientation for S2 would point it into the solid. And so we actually use the negative of N2, so it points inward. Then we end up with the divergence theorem giving us that the triple integral of the divergence of f dv is equal to the flux of f. And that can be expressed as a double integral over s of f dot n ds, which is then broken down into two double integrals over s1 and s2, both of which give us f dot n, but in the case of n2, it's negative n2. So this is the surface integral over s1 of f dot n1 ds minus the surface integral over s2 of f dot n2 ds. And so in this way we can extend to non-simple regions.